Now we are going to talk about maximum margin classifier. And again, this is based on like those decision boundaries which we were discussing for nearest neighbor. But we'll see like how we can actually learn them efficiently given a training data. So in nearest neighbor, there was no training involved. But in this case, we will perform some training so that those decision boundaries are actually learned. Okay. Now, the decision boundary, like what kind of decision boundary you have, that in some way defines what kind of classifier you will have. So the most basic could be a linear classifier. And the idea is you will have a linear boundary, something like this. And like if it's a line, as we discussed earlier, you just need like two parameters to define this line, right? The slope of this line and the x or y intercept of this line. And just those two parameters define this straight line. So to learn a linear classifier, you only need to learn two parameters. Now, most of the time, what will happen is linear classifier might not be sufficient. And later we will see like how we can improve that further and introduce non-linearity into your classifiers. But let's hold on to that thought that will come into picture later. For time being, let's just focus on linear classifiers. Now, the question is, when we're trying to learn these lines, what should be the approach? Okay, so let's look at this example. In this case, again, we have two different categories. These are solid dots. These are hollow dots. All right. Now, we can draw this line. And again, as I said, a line, you just need two different parameters. The y-intercept and slope of this line. That's it. So this decision boundary looks like fine. So if you evaluate this classifier or this linear classifier, it will give you a perfect score on these training samples, because it's always correct for all samples. It's actually making the right decision. Okay. Again, this is also perfectly fine. Both will have 100% accuracy. This is also right. Now the question is, since there are so many solutions available, what is kind of a best solution among all these lines? And that's what we are going to do in this maximum margin classifier. Okay, so the question is, which is the best? So the approach to this is, what we will do, we will not just learn this line which separate these two different class categories. We will also try to maximize the margin between this boundary and the training samples. Okay, so let me try to explain what this margin is. The black line is the decision boundary. All right. And if you look carefully, the orange patch, okay, so that patch is actually extending from this decision boundary towards the classes. So it's extending towards left, and it's also extending towards right. And it will keep extending unless it will touch like any training sample. So in this case, it's touching this sample. And in this case, it's touching this sample, which means that this yellow or this orange patch over here, that's the area where you don't have samples from either like the solid dots or the hollow dots. Okay, and this space is actually called margin. Okay, how much bandwidth or how much space you have left between the decision boundary and the closest sample for either of these classes. Now the goal is we want to maximize that margin, and that's what this maximal margin classifier will do. The name says it all. All right. Now that was one. If you look at this one, this looks pretty cool, right? Again, the center line here will be the decision boundary, which will always be at the center of this patch. And this is like the closest point. Okay. And again, this is the closest point. This is the closest point from the decision boundary. And in this case, you can see like the margin is much bigger as compared to this. So in maximum margin classifier, what we want is we want to maximize these margins. And that's what we optimize when we train our classifier. As I said, like training is involved here. Okay, so this is kind of also like a very simple form of, you can say, linear support vector machine. Again, we'll talk about that later. There is some confusion in nomenclature, but we'll try to clarify that. Okay, so the black line over here is your classifier, and the boundaries of these margins, these are called support vectors. Okay, so these support vectors are something which are exactly touching your training samples. Okay, so the idea is you want to maximize the distance, or you can say like the perpendicular distance between your classifier, or you can say like the classifier line you have, and the support vectors. Okay, so, and again, let's see like how that can be done. Again, we won't dive too much into that, how we can optimize those equations, just the intuition, because again, optimization, that's like a separate topic, and it will take a long time. So don't worry about if you don't understand the actual optimization process, but try to understand the high level idea. Okay, so these SVMs, I think they were developed, I think in 1990s, and since then they were like very popular until 2012, after which deep learning actually just swept them out. Okay, so there's an interesting story as well. So during these 1990s, like researchers were also working on developing neural networks, right? But these support vector machines, they were working really well, and they work really well even today. Okay, it's not that they're not working so well. So they are very, very powerful. And in some of the cases, like where we don't have a lot of data, still I think SVMs can outperform your traditional CNNs, but that's like a separate topic. Let's not go there. So the story is like in 1990s, researchers were working on both these support vector machines and also neural networks. But again, back then we didn't have like a lot of data. We don't have a lot of computation power. So neural networks were kind of going very slow. But SVMs, we don't need a lot of data, right? We can quickly train. We can just optimize your simple parameters, and they really work like very well in all the scenarios. And I think that's the reason, like the deep learning era, which we are seeing, it was kind of delayed, because we might have seen that pretty soon. We waited until 2012, and the reason is like the support vector machines. So after 1990s, like 20 years after that, like everyone was just focusing on support vector machines. A lot of research. But then again, they are suddenly gone after 2012. So now everyone is focusing on deep learning. But I think now it's time to actually go back, and somehow I think there is a way to combine both of these together. We are looking into some of that in our research as well. But still, I think deep learning, because we have data and computation power, so it's kind of questionable, like whether we should go back or not. But anyways, so that was the story. Now, the timeline, how it goes is, first we had like maximum margin classifier, which we'll talk about first. And all of these are kind of related, because in all of these, we are trying to learn this decision boundary, where we're trying to maximize that margin. Okay, then we have a support vector classifier, and then we have support vector machines, all of these related. So we'll try to cover each of these in three separate segments. So let's first go to like a max margin classifier, which we briefly covered earlier. Okay, so the idea is, what we do, we try to learn this hyperplane. And this hyperplane, in case of your Euclidean space, which is two-dimensional space, it's going to be a 3D line, or you can say like a plane, right? A 3D plane. And okay, no, sorry. So if it's a 2D Euclidean space, then you just need a line, right? So that's the first point. And it will be a 1D line, right? You will need two parameters for that. If it's like a three-dimensional space, the hyperplane will be like a 2D plane. And similarly, if you have a p-dimensional space, which is usually the case because your features are most of the time high-dimensional in high-dimensional space, so you will need like a hyperplane which will have dimensionality p-1, and that's all what we need to learn to get this maximum margin classifier. Okay, so the general equation for your hyperplane can be represented as this equation over here. Okay, so all these coefficients are parameters, and these x1, x2 are like corresponding to different dimensions you have in your space. For example, if it's like a 1D line, which is in two-dimensional space, something like this. As I said earlier, for a line in 2D space, you just need two parameters, the intercept. So this beta 0 is the intercept. Okay, so that's the first parameter. And then you need the slope of your line. So this beta 2 is actually, it's not exactly the slope, but you can say, okay, this could represent the slope because you can compute slope using this parameter. So it controls your slope. Okay, so in case of 1D line, you only need these first two terms, beta 0 plus beta 1 times x1. And that will define your one-dimensional line. And similarly, if you increase the dimensionality of your space or your features, you can keep adding more dimensions. But in general, this will be the representation of your maximum margin classifier. That's how the hyperplane will really look like. Okay, so yeah, why we have x1, x2? Okay. So yeah, so this equation will, yeah, I don't know why we have x2. I think this should be in two-dimensional, right? Because for one dimension, you don't really need like both of these. But anyway, so that's fine. This is the general formulation, and you know like how it will look like in n-dimensional space. It's just a hyperplane. All right. So now what will happen, what you're going to learn is you will have your training samples. Let's say if it's a binary classifier, you have blue dots, you have these purple dots here, and you're going to learn this line, or you can say hyperplane. And there are many, many possibilities. So we want a hyperplane which will maximize these margins. Okay, so the distance between this hyperplane and the support vectors should be maximized. All right, so what we can do is we just try to maximize this margin. All right, and these are the constraints, like your training samples. Okay, so okay, let me go over one more step. So if this is a hyperplane, then if we use this training sample, if you try to put on this equation, it will give you negative value. All right, and if you put like these points over here or these coordinates, it will give you positive value. So what we want is we want to satisfy that constraint, that if we have like this margin over here, it should always be towards the right. So all purple dots should be towards the right, and all blue dots should be towards the left. Okay, considering that constraint, so that's the constraint which we have here. We are just placing all the training points in the equation of your hyperplane. So they should be like greater than m. So m is your margin because they are that distance away from the decision boundary, because m is your margin. Okay, as I said, if the point is directly on this plane, the value will be 0, but we want that value to be m. Okay, so that's what we are optimizing. And then once you have this equation, you can just use any optimization technique to actually find these values. So the values you're looking for is all these betas, which define your hyperplane. Okay, so that's fine. And as I said, don't worry about like how to do the optimization. That's like a separate topic altogether. Just try to understand the concept of how this classifier works. Now let's try to figure out like whether this kind of classifier will be robust towards noise or not. And that will motivate you to go further and study, let's say, the support vector machines. All right. Now, let's say your after optimization, you found this as your hyperplane, and you can see that it's kind of maximizing the margin, right? The distance from this purple point and this blue point, that kind of is the maximum. But now let's say you have another testing sample, which is at this point. So this is kind of a corner case as well, because if it has to be blue, it should not be close to purple, right? But let's say if it is there, then this dash line, which we actually learned using that optimization, will completely fail, because it will say this is a purple dot. So in this case, you can see this hyperplane is actually working. Okay, in this case, the blue is actually on the other side. So you can see that If you have more and more samples along this decision boundary, then your classifier is actually not very robust to those kind of samples. Because this is a very drastic change, like going from this classifier to this classifier. You can see like the slope actually changed a lot. Okay, so it's actually very sensitive to what kind of samples you will have in this boundary. And of course, it's not sensitive to like points which are far away from the boundary, which are kind of like simple or trivial points. Okay, it won't change like, so if your point is beyond like these boundary points, which are kind of, you can say like at the frontier, then the classifier will never be affected. You can have as many points as you want.